In Colligative Properties 1, I talked about these 4 colligative properties: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure, and we talked about the 4 expressions for those 4 properties. We also made the stipulation that those were for non-electrolyte solutions, and now in this video we're going to talk about what happens if the solutions are electrolytes. Alright, but first let's look at the non-electrolyte solutions again and look at what the concentration unit is in each of them. And this is the concentration of the solute. They each have some sort of unit of concentration in them. Vapor pressure lowering has chi solute, which is the mole fraction. The boiling point elevation has a small m, which is molality. Freezing point depression has the same thing as boiling point elevation, and that is molality. And finally, osmotic pressure has capital M, which is molarity. So they do all depend on solute concentration, but not always in the same form. All right, now let's look at what happens if you have an electrolyte. Okay, so as a solute, electrolyte is something that can separate into ions. And what happens is we talk about something called the Vant Hoff Factor, which is given the letter I, sort of a script I, and it is represented by the fraction of the actual result divided by the result for a non-electrolyte. So it's sort of a correction term for how much different a solute acts than a non-electrolyte. And that is approximately, and it can be approximated as, the number of particles, which in this case would be ions if they're electrolytes, in solution. For example, if you have sodium chloride as your solute, when you put it in water in particular, it will separate into sodium plus ions and chloride minus ions. So for every 1 unit of sodium chloride, you actually have 2 units of particles. So we say that I equals 2. If you have magnesium chloride, in that case, it separates into ions of magnesium 2 plus and Cl minus, but you get 2 Cl minuses for a total of 3 particles for every 1 formula unit of magnesium chloride. So I is equal to 3. In other words, the actual result depends on the number of ions in solution, not if it's a non-electrolyte like sugar, it just stays whole as sugar, but if you put an electrolyte in, it separates into more particles, so it acts like more solute. So this correction factor is for that. And we can look at something that is not an electrolyte, like urea, and it won't separate into anything, so I will be 1 for things that are non-electrolytes. So this leads us to make corrections in our 4 equations above for electrolytes. We simply put in our I. So we take the original expression, the vapor pressure lowering is equal to the chi for the solute, and we put an I in there, times I times P naught. And usually the I is written first. I times chi solute times the pure vapor pressure. For boiling point elevation, you simply put an I in the expression. Freezing point depression, put in an I. So they all are multiplied by this factor, which is approximately the number of ions in solution. And finally, osmotic pressure. Okay, so the expressions are exactly the same as non-electrolytes, but with an I in them. All right, and these I's are only approximately the number of particles. So We call those the ideal Vant Hoff factor. They're the ones that you calculate. Okay, so if you look at HCl, it separates into H plus, Cl minus. It's a strong acid. So its calculated Vant Hoff factor would be 2. The actual measurable, experimentally measured I factor is the non-ideal one. It's the real one. So the actual is 1.9. And that's because that in reality, it doesn't quite have as much effect as you would calculate based on the number of particles. For FeCl3, iron 3 chloride, you get an Fe3 plus ion and 3 Cl minus ions. So you'd expect the ideal Vant Hoff factor would be 4 particles. The actual measured one is 3.4, so it is somewhat less. And sodium nitrate, that has a polyatomic ion, so it separates into a sodium and a nitrate, 2 ions. So your ideal Vant Hoff factor would be 2. We can use this to compare boiling points for various species. So look at this problem, which would have the highest boiling point in water, because in water the electrolytes will separate. 0.1 molar sodium chloride, 0.1 molar urea, or 0.1 molar iron 3 chloride. And the way you think about this is the highest boiling point. Now, when you add solutes to water, the boiling point is elevated, so it gets higher. So the highest boiling point will be the one that has the largest elevation, which means the one with the highest I, as long as they are the same concentration. So we can talk about what their ideal I is. So the ideal I for sodium chloride we said was 2. The I for urea, it's not an electrolyte, so it's just 1. And I for iron 3 chloride was 3. So we can also talk about an effective molarity or effective concentration. Now remember, the boiling point is related to the molality, not the molarity. But if molarity is increased, so will molality be. So it'll be the same trend in molality. So the effective concentration, if I is 2, then the effective concentration is 2 times 0.1, so it's 0.2 molar when you have sodium chloride, because it separates into 2 particles. For urea, it's just the same. It's still 0.1. For iron 3 chloride, it's 0.1 times 3. 0.3 molar is the effective concentration, which means that the highest boiling point will be for the one with the highest effective concentration, which will be the iron 3 chloride. This same thing will occur for the other colligative properties. Your freezing point is depressed, so the lowest freezing point will occur for also the things with the most effective concentration. Okay, so that'll give you the lowest freezing point. It'll also give you the lowest vapor pressure, since vapor pressure is lowered by particles in solution, and it'll give you the highest osmotic pressure. So the larger your I is, the greater these trends will be. All right, so these we're comparing 3 that are the same concentration. What if we compare 3 that are different concentrations? Okay, so let's say we have 0.1 molar magnesium chloride compared to 0.2 molar sodium nitrate compared to 0.3 molar glucose. Which one will have, and you can ask any of these questions, the highest boiling point, the lowest freezing point, the lowest vapor pressure, or the highest osmotic pressure? Any of those you could ask. So let's just say we're asking the highest boiling point again. Okay, so we're looking for the greatest effective concentration. Well, let's look at the I's. We have concentrations. Let's look at the I's. The I for magnesium chloride was 3, so its effective concentration is 3 times 0.1, so it's 0.3 molar. Sodium chloride, that has an I of 2. Multiply I by the concentration and you'll get 0.4 molar, so that one would be greater. Sodium nitrate would be greater than magnesium chloride. Glucose has an I of 1, so 0.3 times 1, 0.3 molar. So the one with the greatest effective concentration was the sodium nitrate, not the one with the greatest concentration, nor was it the one with the greatest I. It's the one with the greatest product of the two.